Assalamu alaikum. Welcome to lecture number 20 of digital signal processing. In this lecture, we will discuss in more detail regarding discrete Fourier transform, which is the robust technique to analyze any real-time signal. Here you can see the analysis equation as well as synthesis equation of a discrete Fourier transform. And the notations are also written on this slide. X of k is basically the frequency domain output, or we can say the kth DFT output component, where k is the index of DFT output. So we have to vary k from 0 to n minus 1, just as in the conventional case. X of n is the original samples or sequence, or which is provided to us, for which we will calculate the x of k, where n is the time domain indexing and capital N is the number of frequency points in DFT output, or the number of samples or number of points for which we are computing the DFT. So you can say that DFT is one of the most useful and robust technique to analyze any signal and to actually know the frequency components present in that signal. We can apply this robust technique, or I can say it is one of the most common and powerful procedure that is encountered in the field of DSP. So this basic DFT technique is the one which can be used to analyze any real world signal, and that signal must be periodic or aperiodic, no matter. It can be applied to both periodic as well as aperiodic signal, but signal should be discretized. So to apply this technique, we have to first convert the continuous and aperiodic real world signal into discrete time domain, after which we can easily apply the DFT technique. Also, we can apply DFT technique only on the finite duration or finite sequence, or I can say finite number of samples. So it cannot be applied to infinite samples if your signal is aperiodic and it is also contains infinite values. So you have to take some of the sample values to compute the DFT, because DFT cannot be applied on the infinite duration sequence. So basically DFT has nothing to do whether the given finite duration sequence is coming from some periodic signal or not. DFT treats every signal in a similar manner. So it doesn't matter whether the signal is periodic or aperiodic. Same procedure or the same technique will be applied to calculate the frequency spectrum by using discrete Fourier transform. In this slide you can see we are going to solve a numerical in which a sequence is given as x of n and the sample values are given as 1100. So 4 samples are given to us and the indices at first value, which is n is equal to 0, and it is asked to compute 4-point DFT. So what is meant by this 4-point DFT? If we can actually take DFT for n number of samples, and n must be some integer which results from 2 raised to power n. So here you can see there are 4 values, so we can also solve this numerical by taking 2-point DFT for the first 2 samples and 2-point DFT for the last 2 samples, and we can combine the results to compute the DFT of entire signal. Or in other way, we can simultaneously take the 4-point DFT of this sequence. We can assume another case in which we are provided with 16 samples, so we can take 8-point DFT for the first 8 sample values and again 8-point DFT for the remaining values. So in this way we can solve the numerical which is having 16 samples by taking 8 points a DFT, or if we want to do it simultaneously we can solve it by taking 16-point DFT, so it will be done all at once. So in this problem it is mentioned that we have to solve this numerical by using 4-point DFT, and the sequence is also contains 4 number, so we will take the entire sample values to compute the DFT. Here you can see the analysis equation of DFT, the standard analysis equation. This analysis equation is basically the conventional method of computing DFT. However, we look one of the other technique which is more simpler and easier, which is the matrix formulation of DFT and the analysis of any signal with the help of matrix equations. So this one is the conventional procedure. Just we looked at different techniques such as CTFS, CTFT, DTFS and DTFT. There we learn to compute the frequency spectrum of signal by using these analysis equations and synthesis equation in this conventional form. So again we first try to solve this numerical by using the conventional equation, then we will look at the other technique which is matrix formulation of DFT. So in this example we are proceeding with the conventional equation of DFT. So you can see that analysis equation is given to you, and again the order of solving of this equation is, first you have to fix the capital N, which is the number of samples or the number of points for which you are computing DFT. Then for the small n you have to vary it to 0 to n minus 1, and the third step is to vary k from 0 to n minus 1. So these three steps or order of solving is same as we learned in the previous techniques. So first of all we are putting capital N equals to 4 because we are computing 4-point DFT for 4 sample values. So this is the standard equation, and we have placed the value of n is equal to 4. Now the equation becomes like this when we try to expand it with n. So x of 0 multiplied with the basis function where small n is placed as 0, then x of 1, again 1 is replaced here, x of 2, n is replaced by 2 here also, and similar as the third sample. So we expanded this equation. Now we are going to actually put the sample values which are x of 0, x of 1, x of 2 and x of 3, and we know that in question x of 0 is given as 1, so we placed x of 0 as 1, x of 1 is given as 1, so we placed it as it is, and x of 2 is 0 and x of 3 is again 0. So by these last two terms will turn up to 0, and you also see that, you can also notice that this basis function also becomes equal to 1 because e raised to power 0 is 1. So here you can see last two terms become 0, and if we further simplify this, then e raised to power 0 is basically 1 as discussed. So this is the equation which is depending on the variable k. Now we have to vary the value of k from 0 to n minus 1. So first we are putting the value of k as 0. So when we put k as 0, then equation becomes like this: 1 plus 1 is 2, and we get x of 0 as 2. Now second step, k is varying from 0 to n minus 1, so k is vary from 0 to 1. Now in this equation we are putting k as 1, so you can see that we will get 1 minus iota. Same, you can apply the same identity: e raised to power iota theta is equal to cos theta plus iota sine theta. So you can expand this basis function and you will ended up with this minus iota as written in this slide. So this is the identity. I have added this in the presentation also. Now when we put the value of k as 2 in the function, the basis function becomes e raised to power minus iota pi, and we have to expand it with the identity cos pi minus iota sine pi, and we ended up with minus 1. So 1 minus 1 is basically 0. So x of 2 is calculated as 0. Now x of 3, again we have to apply the same identity cos theta minus iota sine theta, and we will get iota in the result. So 1 plus iota is the result of x of 3. So capital N is 4, and we have to vary k from 0 to n minus 1, which is 3, and we already done with the expansion of k till 3. Now we are actually combining all these values and put it in the sequence. So x of k sequence becomes 2 comma 1 minus iota comma 0 comma 1 plus iota, and the indices is on the first value, just in as in the original question. So you can find the magnitude and phase spectrum values also from this sequence. The magnitude becomes 2 comma under root 2, 0 comma under root 2, and the phase spectrum is like this: 0 minus 45, again 0 and 45. Now we are going to plot the magnitude and phase spectrum of this signal. The sequence of magnitude and phase spectrum is shown in this slide. So first of all, we are going to plot the magnitude spectrum. On x-axis we are taking k, and along y-axis we are taking c of k or x of k. Both are the same things. So we have total 4 values, so we can take from 0, 1, 2, 3, and now we are plotting the first value, which is 2. So we have marked the y-axis. First value is marked as 2. The second value when k is equal to 1 is marked as under root 2. The third value is 0, and the fourth value is under root 2. So this is the magnitude spectrum of the provided sequence. Now plotting the phase sequence, again we are taking k on the x-axis and angle on the y-axis. So again k is varying from 0 to 3, and along y-axis we are taking minus 45 to 45, because we have to plot these values. At k is equal to 0, we have 0 angle or 0 degree. At k is equal to 1, we have minus 45, so we plot it accordingly. At k is equal to 2, we have 0, and again k at k is equal to 3 we have angle 45. So in this way we can plot the magnitude and phase spectrum separately. Another important thing is the frequency resolution of the DFT output. This concept can easily be understood if I ask you to plot or tell me the actual frequency components which is present in any provided signal. So you will not answer me in terms of k, because k is just an integer value, it is not representing the actual frequency. However, if you want to represent or want to know the actual frequency which is present in some specific signal, so you must know the frequency resolution of DFT output. That is the resolution by which the two spectral lines are separated with each other. So this is basically the frequency resolution. And how you can find the frequency resolution? Formula is written on the slide. Frequency resolution is denoted by delta F, and it is simply the ratio of Fs over n, where Fs is the sampling frequency and sampling frequency is the one on which your continuous time signal is sampled to obtain the discrete time signal. So that is basically Fs, and n is the number of points for which we are computing DFT. So by putting the values of Fs and n, we actually get the value of frequency resolution, which is the distance between the two consecutive spectral lines. And if we want to know the exact frequency, then we will simply multiply k with that frequency resolution. I have added the question which relates to the previous example or numerical which we already done, and the question is, consider the x of n in the previous question was sampled at every 0.01 second. So this is basically sampling period is given, which is 0.01 second, and we have to find out the frequency components in the hertz. So actually we are required to determine the actual frequencies which are present in that signal. So for this we have to first find the frequency resolution, which is delta F is equal to Fs by n. And how we can determine Fs? Because sampling period is given, which is 0.01, so we can just divide this 0.01 by the factor of 1, or we can say we can take its reciprocal to get the sampling frequency. So when we take the reciprocal of this 0.01, we will get 100 as the sampling frequency, and we know that the number of samples or n was taken as 4 in the previous example. So by this way, dividing 100 by 4, we actually get the frequency resolution, which is 25 Hertz. So the 25 Hertz is the frequency resolution, or the distance between the two consecutive spectral lines. And by this knowledge, we can actually determine the actual frequencies that are present in that signal. We know that k is varying from 0 to n minus 1, which is 0 to 3. So first put k is equal to 0. So we will get fk as 0. So 0 Hertz is the first component which is present in that signal, which is the DC component. Then when k is equal to 1 and delta f is again 25, so we will get 25. So 25 is the first harmonic or first analysis frequency which is present in that signal. Second frequency is obtained by placing the value of k as 2. So when we put k as 2, we will get fk as 50, and similarly for f3, which is 75 Hertz. So by the knowledge of frequency resolution, we actually know what are the actual frequencies which are present in any provided signal, and we can say that there is a 0 hertz component or a DC component which is present in that signal. There is a 25 hertz component, there is a 50 hertz component, and there is 75 hertz component also present in that signal. I might add another very interesting point here, which is if you look at the frequency values we are getting, so 0, 25, 50 and 75 hertz are the frequencies which is present in that signal. But if we look at the sampling frequency, so it is 100 hertz. Please look at this number, 100 hertz, and it is actually the sampling frequency. And if we refer to the Nyquist criteria or sampling theorem, then we actually conclude that the maximum frequency which can sampled correctly with this sampling frequency is 50 hertz. So we can say that the last component, which is 75 hertz, is actually the aliased version of some of these values or some of these spectral lines which are present on these particular frequencies. And how we can actually determine the exact aliased frequency? We can use the formula we learned in the ADC concept. So you can refer that formula to obtain the aliased version of 75, which is obviously 25 hertz. So basically only three frequencies are actually present in that signal, because fs is 100, so fs by 2 is 50. So the maximum component or maximum frequency value that can reconstructed correctly at this sampling frequency is 50 hertz. So basically we will see the spectrum to only three spectral lines, and we will discard all the remaining values because they are the aliased version or simply the repetition of the same frequencies. That is the very reason you have noticed we are getting 1 plus iota and 1 minus iota, and both are the conjugate pairs. So both are the aliased version, means 75 is the aliased version of the same factor which is present at 25 hertz. So I hope you understand this concept. Another interesting topic, which is the matrix formulation of DFT. The analysis and synthesis equation we learned so far was the conventional analysis and synthesis equation. However, the process can be simplified and the computation can be actually simplified and speed can be improved by using the matrix method of computing DFT. So what is that method? You can see we have two equation. One is the analysis equation and second one is the synthesis equation, just as in the previous cases, and both the equation are in obviously equation form. But if you look at the variables used in the equation, so these equations are basically representing a vector or matrix. So you can see, if you see the analysis equation, then x of k is equal to summation of n is varying from 0 to n minus 1, summation of product between the two matrices. First one is x of n, which is the original signal, and the second one is the transformation matrix, which is w of n. And you can see that wn is this type of matrix. And if we want to synthesize our signal, we can use this equation, in which we have used the inverse of w. And what is basically w of n? It is simply the basis function e raised to power minus j 2 pi over n. So whatever the value of n here, we will put the same value of n here to get the value of that particular value of w. So here you can see that we are actually computing the numerical values of W4. So when W4 is used, the question is this, and when we use W2, W3, W4 and W5 so on. So it depends upon the number of samples in actual signal. Suppose 4 samples are provided to us, and we are asked to calculate the DFT by matrix formulation method. So as we are provided with the 4 number of samples in the signal, so we will take W4 as 4 by 4 matrix. So we will use W4 there. And similarly, if x of n will contain 5 sample values, then we will consider 5 by 5 matrix of W, which is W5. So the dimension of this transformation matrix depends upon the number of samples which are provided to us for computing the DFT. So this W4 matrix can be used to compute the DFT for 4 samples or sequence which contain 4 samples. So in this question we are asked to compute the numerical values of W4. It is very simple. We know that for W4 there must be a matrix which have 4 rows and 4 columns. So by putting the value of W with respect to the basis function, and basis function you all know is e raised to power minus j or iota 2 pi k n over n, capital N. So we have to vary small k, small n, and capital N is always fixed, which depends upon the number of points we are going to take the DFT or the number of samples. So here n is fixed as 4, and we have to vary the small k and small n, just as in the numerical we have solved it with the conventional equation. So there we are varying the k and small n from 0 to n minus 1. So likewise in this matrix also we are varying small k and small n from 0 to n minus 1, which means 0 to 3. So if we apply the basis function at each of these values, we will ended up with these values. So you can expand any of the matrix with the basis function e raised to power minus iota 2 pi small k small n over capital N. So when you solve that basis function, you will ended up with this values, or with this matrix contain these values. So this matrix is basically we will use when we are computing the 4-point DFT of any signal provided to us. So we will see it in the later numerical, in which we will analyze a real-time signal or real sample values, and we will compute the DFT by using this transformation matrix W4. So in this question you can see it is asked to find x of k, which is obviously the frequency domain analysis or frequency domain view for the signal 0 1 2 3 by matrix method. So and indices is at 0 value, which is n is equal to 0. So 4 values are given and we have to compute with the help of matrix method. So we know that we have to take W4 as 4 values are given, and we are computing 4-point DFT, and the values of W4 is calculated in just in the previous slide. So the same values are here, and what we have to do, we have to apply the equation, simple analysis equation, and by applying the analysis equation we will get the answer. We are simply multiplying this transformation matrix with the original signal values, so we will get the values or frequency spectrum, which is capital X of 0, capital X of 1, capital X of 2, capital X of 3. Here capital X is denoting the frequency domain and small x is denoting the time domain. So in this way you can see the solution is achieved within 2 to 3 steps, and how fast we achieve the solution, you can compare it with the conventional equation or conventional pattern we have followed to solve another numerical. So if we apply this technique to that numerical also, we will end up with the solution within 2 to 3 steps, which will require no such time. So we have learned the technique discrete Fourier transform, both its analysis equation as well as synthesis equation in a conventional manner, as well as one of the robust technique or robust procedure, which is the matrix method, how we can calculate the DFT of any signal with the help of matrix method. And we concluded that matrix method is much simpler and easier as well as faster as compared to the conventional method. So we will prefer to solve numerical by the matrix method. So in this slide we are going to learn the computational analysis of endpoint DFT. This is basically the total number of computations which are required in calculating any endpoint DFT. So by this figure we came to know the actual processor speed which is required to run the algorithm, because obviously if we are computing too much then we will require a faster processor. So by the computational analysis we actually came to know the actual number of real and complex computation. So you can see, and you can also observe from the previous slides, we are obtaining different results, and results in the form of real number as well as some complex numbers. So our processor has to add or multiply these real and complex values, and by multiplication you know that multiplication is nothing but the addition. So actually processor has to do number of complex computation and number of complex as well as real computation to actually compute the endpoint DFT. So the formula for total number of complex computation is 2 raised to 2n raised to n square minus n, and the total number of real computation in endpoint DFT is 8n square minus 2n. So here is a question or practical example in which we are calculating the real and complex computation required to perform 1024 points DFT. So by applying the formulas for complex computation, we apply a simple formula 2n square minus n, and we place n as 1024, so we will get 2096128. So this particular number of complex computation are required to perform 1024 point DFT. And same is the case with the total number of real computation, which is equal to 8n square minus 2n. So we will ended up with 8386560. So we can actually add the complex plus real computation to get the total number of computation required to perform 1024 point DFT of any provided signal. So by the final answer, we can actually select the processor speed for which is suitable to compute or to handle this large number of computations. In this slide, I have added an example. So this example is very much realistic, in which some real-time scenarios are given and we have to suggest the processor speed that can be used to perform DFT in real time. So, and the question is, the incoming data rate or data throughput is 512 samples per second, and the length of DFT operation is also 512 samples. So what we have to do, the processor can handle one complex computation per clock cycle. Okay, suggest the minimum processor speed that can handle DFT operation in real time. So some data is provided to us and we are required to calculate the minimum processor speed for that particular DFT operation. So the question is very simple, as well as its solution. We have to calculate the processor speed, and processor speed is as simple to calculate as a multiplied by b multiplied by c. And what are a, b and c? The units are written on this slide. A is computation per DFT, b is simply DFT per second, and c is cycles per computation. So you can also cancels the dimension which are common. So DFT is cancelled with DFT. Basically this DFT and DFT will cancel each other, and this computation and this computation will cancel each other, and we will ended up with cycles per second, which is actually hertz, and hertz is basically representing the processor speed. So we know that the processor are always rated in hertz. So we actually have to extract the value of a, b and c from the given data, and after putting the values of a, b and c, we will get the required processor speed. So I want you people to do it by yourself. It is very simple. I have mentioned you have to calculate a, b and c. A is computation per DFT. You have to search it from the given data, what is computation per DFT, and b is DFT per second. Again you have to look at the given data, what is the value of DFT per second, and the third is cycles per computation. So it is given in a very straightforward method. You can see the processor can handle one complex computation per clock cycle. So it means one is computation and clock cycle is 1. So both these numerator and denominator is 1. So if it is like that, the processor can handle two complex computation per clock cycle, then you have to write 2 in the denominator, because 2 computation and per clock cycle means 1. So in that scenario you will have the value of c as 0.5, but here c is 1 because processor can handle one computation, denominator is 1, in one cycle. So c is basically 1. Now you have to look at a and b, and after extracting the value of a and b, multiply these three values to get the processor speed. So good luck for this numerical.